Hey everybody, welcome back to Calc 3 Online. I wanted to start off and kind of revisit this. So last time I said we will prove this identity that relates to the angle kind of between two vectors and dot product. And that's just what I want to start off with today. And first I kind of want to go back to this idea with how you add vectors. So, if we take s and add to it t, we would get this resultant vector s plus t. So along that vein, if we have two vectors a and b, let's call this a, and let's call this b. Actually, I'm going to move my a to here. This dot product identity is going to help us find that angle. And to really prove this thing, we're going to actually create a triangle just like I have over here. And to do that, the triangle I actually want to create is not just closing this off, but I'm going to say that is about negative b, right? Because that's how these vectors would work. If you go in that direction with that magnitude, that's b. So if you go 180 degree rotation on it, that would be negative b. And so if you take this vector now, this blue vector would be a minus b. That would be similar to how I get s plus t over there. So what we basically have is actually a triangle problem, and the way to kind of get some magnitudes and cosines in is really using something back from Algebra 2, which I will kind of just write up here. And really you can think of it as I always think of this thing as the generalized Pythagorean theorem. It's your law of cosines, right? So if I use a and b as the vectors, this a and b, is a and b, and theta is the angle here, then c here from your law of cosines would be a minus b. That would be the triangle that we're working with. It could be the same triangle up here also. You could do the whole problem that way too, but we're going to do it with this one. So c is a minus b, and so c is, this is a distance, right? It's the length of that side of the triangle, so it's the magnitude, the distance part, right, of the vector. So we're going to have magnitude of a minus b squared equals the magnitude of, that's a squared plus the magnitude of b squared minus 2 times the magnitude of a, and I'm running out of room, times the magnitude of b times the cosine of theta. And this is where we're going to use a little fact from last class, so I might kind of just tuck this in over here. So remember, the magnitude of any vector squared is equal to that vector dotted with itself, and we proved that last class. So that means we can turn some of these magnitude squares into things like a minus b dotted with a minus b, which would equal a dot a plus b dot b. And then we've got, again, I need a little more room here, minus 2 times the magnitude of a, magnitude of b, cosine of theta. And dot products are nice with distribution. So you can you can basically double distribute this, and you're going to get a dot a, you're going to get minus 2 a dot b's, and then you're going to get a plus b dot b, which equals a dot a plus b dot b minus 2 magnitude of a magnitude of b cosine theta. And this is nice because now these are scalars, right? The dot product is scalar. So this number here is going to cancel with this. This number is going to cancel with this. And actually, I guess you can also cancel the -2 part from either side. And so then you're going to have a dot b is equal to the magnitude of a times the magnitude of b times the cosine of theta. And that proves it. So if you've never seen this little thing before, sometimes in math when we prove something, we put a little box at the end of it, just to kind of say, we're done. But that's it. So this really is something that we will use a lot. There's actually an important one that relates to this for sine as well. And we will get to that in a few classes. But for right now, this is one that you definitely want to kind of file away. What I want to talk about today is actually something related to a dot product, but it isn't super clear how it's related to a dot product. It's something called projections, and it's almost best to explain this really with some physics concept called work. So if you haven't heard of work before, basically the way I always think about this is if you have some ramp, and my ramp is too big there, and say you have some like box or something, and you need to push that box up the ramp, that is going to require more work than if you have a ramp that's here and the box is here and you want to push the ramp down, right? So the name basically is it's pretty logical. Like we have more work here. It's just harder to basically do this. More work, less work. And if you took a physics class, you might have learned that work equals force times the distance. And in vector world, it's actually the force vector dotted with the displacement vector. And actually, I'm going to move this over here. So we got work equals the force vector dotted with the displacement vector. And in this picture, I'm going to call this my force vector. And I'm going to call this whole thing down here D. Let's do lowercase d. And I am going to call this vector here just V for no good reason. And what we're actually going to kind of show is by working through kind of just some dot product identities and what the cosine of that angle in there is, I can actually build up the thing we call the projection formula for two vectors. And so we'll start with V, and this vector V is equivalent to the magnitude of that vector times, let's do lowercase d again, times a unit vector for d, right? Because if the vector v here, whatever the unit vector is, then you scale it by the size of v, you would end right there. That's the idea. So unit vector in d, maybe it ends here, and then we multiply by the magnitude, we'd end right there. And the unit vector in d is just using the definition of a unit vector. It's going to be the vector d over its magnitude. And this is probably where I want to kind of make a little aside. So we know based on that formula that we proved on the last slide that the cosine of theta is f dot d over the magnitude of f magnitude of d. We also know, though, that the cosine of theta, if we just use like triangles, right, it should be just, this is just like using SOHCAHTOA, literally. We would have the magnitude of v over the magnitude of f, right? It's just, this over this is the cosine of that. So those two are equal. We'll use those here in a second. And so if I have a v, right, I could swap that out for this one here, just solved for v. So that's cosine theta times magnitude of f. So I'm going to do that. I'm going to write magnitude of f times cosine theta d over magnitude of d. And now I'm going to also swap out that cosine theta, right? We know by this that the cosine of theta, I'm going to get rid of some of that. The cosine of theta is just f dot d over magnitude f magnitude d. That whole thing is just cosine theta, and then we got d over magnitude d. And some stuff's going to cancel, right? We got a f, magnitude of f, and we could also really kind of simplify this part because that's the same thing multiplied, so we could just square it. So what we could rewrite this as is f dot d over magnitude of d squared, and all of that is times this vector d. And this is actually the formula for the projection of f onto d. And I have this written out in the next slide here in a second. But really what we're doing with this is we're, in a sense, we are scaling how big this is. It's going to, in this case, it shrinks, right? This is a smaller vector than this one. But some of that force is basically kind of lost in a sense. And it's going to become, it rescales d down to this size v here. So this vector v is this scalar of d, basically. This whole thing is a scalar, right? Because that part up there is scalar. This is definitely just a distance squared. So this number shrinks d. And that would be what v is. It's the projection of this vector onto, down in a sense, right, onto d. And it's going to then shrink it and give you v here. And so this is the kind of standard way that we write it. We actually do write this projection. We read that projection of u onto v. And then there's a part in here that acts as a scalar. And sometimes, actually, when you project, you might make it bigger. The scalar might be bigger than 1. So you're kind of stretching it out. But sometimes a lot of times it's smaller. Like in this example, it definitely makes f kind of shrinks down to the size of v when you project it onto d. And it is a very different thing if we switch where the letters are. So projection of v onto u would, the uv part of the top doesn't really matter. You just take the dot product. It's going to be the same either way. But then you would have magnitude u, and all of that would be times magnitude of u squared, and all of that would be the scalar for u. And really, it is just kind of like this picture down here shows. You've got the projection of u onto v is, again, shrinking it here to give you a smaller vector. The way to get a bigger one is basically just if the angle, we'll just kind of say here, so if that angle in there isn't acute, if it's obtuse, then the projection will stretch it out. It'll make it bigger, right? And actually, if they're perpendicular, the vector gets lost, right? Because if you, let's kind of do this like here. So if you have a vector u and you have a vector v, and that was 90 degrees, if you project u, so we would write that, project u onto v, right? You're going to lose all of that vector. It basically gets squished down just to that point right there. So this would be actually equal to just like the 0 vector. So just to kind of show you how we do it, I mean, it is a fairly straightforward calculation. If we were going to find the projection of u on v here, we start by just taking the dot product. So we would get 1 times a half, which is 1/2, plus 2 times a half, which is 1. And then we get plus 3 times 1 over root 2, which is 3 over root 2. So that's the that's this part right up here, u dot v. And then the magnitude of v would be, magnitude of v, I was looking at u for a second, is 1 plus 4 plus 9, right? You just square each part, and then you square root, and then you square. So really, it's just, remember again, this is whenever you square a magnitude, it's equal to like v dot v. And all of this is going to be just the scalar on that vector. And I'm going to go grab a calculator. So when I go plug it into a calculator, this part in here, when I plug that in, I get 0.2587. And then we got the vector 1, 2, 3. And so what this means is that the projection of u onto v, since this number in front is a decimal, right, that's less than 1, it is kind of one of these cases right here. Again, where we're going to shrink u in a sense. The projection of u onto v is going to be something smaller. It's scalar in front. This part is always a scalar. This part's scalar. That scalar is less than 1, so it's shrinking it. And you can even just write it this way. That's fine. You could multiply this into every little part here, but it doesn't really make it any more clear what the vector is. In a lot of ways, this kind of tells you a more important thing, that this is, it's in a sense shrinking u when you project it onto v.